Okay, I'm going to try and finish this one that I did in class as well. I have free body diagrams of the two blocks. B is on the left and A is on the right. The next thing I need to do is to find the accelerations of these, and what I'm going to show is using relative positions, relative accelerations, and I'm going to use Mathematica to do it. First thing I'm going to do, things are happening in odd directions, so what I'm going to do is just define some directions for this. So what I'm going to establish an I direction, which normally people think of it as being to the right, so we'll do that, and then we have a J. The next thing I'm going to do, and I'll put it define a direction U along this incline, and then I'm going to put in another color, and I'm going to define a coordinate or direction right here, and we'll call it direction V. So we have a U and we have a V, and I'm going to put the vector U in terms of I and J. So the vector U is going to equal cosine of 30 degrees in the I direction, and it'll be the sine of 30 degrees in the J. I can define V in terms of the I and J. So V is going to equal minus cosine of 20 I and positive sine of 20 J. Okay, so now I'm going to define the positions of the block. So the position, we'll call it P for position of A relative to the ground. So I'm going to find a point, say right here. It's painted on the ground, and I'm going to define the position right here as the we'll call that Y. So the position of A relative to the ground is going to equal a distance Y, and it's in the negative U direction. So that's the position of A relative to G. Position of B relative to A, I'm going to put a point right here, and I'm going to define a distance. We'll call it X. So that would be distance X, and it'll be in the B direction. So the position of B relative to G is going to equal the position of B relative to A plus the position of A relative to G. Okay, so putting that all together, position of B relative to the ground, these are all directions, they're vectors, so I should be careful, I guess, and put bars over them. Okay, so B relative to the ground is B relative to A plus, oops, it would be minus Y in the U direction. And of course there are constants, but I'm not too worried about the constants because I'm going to differentiate this. So then if I differentiate this 2 times, I'll get the acceleration of b relative to the ground is equal to x double dot v minus y double dot u. And the acceleration of a relative to the ground is equal to the second derivative of the position. So that would be a minus y double dot in u. Okay. Now what I'm going to do is put these into Mathematica and show how to handle this kind of stuff when you have vectors. Right, first thing I'm going to do is define my I, j, and k vectors. Okay, so I and j, it's 2 dimensions, so I don't really need k. Then I'm going to define the u vector. Which is up here in blue. And I'm going to define the v. So there's my I, j, u, and v. Now what I'm going to do is define the acceleration. So the acceleration of b is x double dot in the v direction minus y double dot in the u direction. And the acceleration of a is minus y double dot in the u. So now we'll get our forces, and I'm going to sum in the x, or the I and the j. So I is to the right, j is up, so we'll take the vector b, or body b. So here come my force equations. Right. That would be in b times the cosine of 20 in the I, that's all, so that equals mass of b times the acceleration of b in the I direction, which is this piece right here. The forces in the j direction will be in b sine of 20 minus mbg, and that equals the mass of b times the acceleration of b in the y direction. Copy and paste. The other equation is from this free body. So that would be in the I direction, I have minus NB times the, let's see, let me get an angle here. Right, so there's the horizontal. This angle here is 30. The angle, this angle is 20. So this angle here is, let's see, it's 90 between NB and that dash, so this guy would be, let's see, alright, so this angle is 40. Alright, so back to the forces in the x direction. It'd be NB times the cosine of 70 degrees. And I have an NA. It's also negative NA. And that would be let's see, this angle is 30, and so this angle here is 60. So it'll be NA times the cosine of 60. That's in the horizontal, and that's all, so that equals mass of A times the acceleration of A in the x direction, which is right here. Copy. Paste. And then for the y, I have in A sine of 60 minus in B sine of 70 minus mass A times G. Those are all the forces, and that equals mass of A times the acceleration of A in the J direction, the vertical. Copy. And paste. And those are all of my equations. So end it. And let's see, what did I mess up? I only have one equal sign here. So equal, equal. There we go. And then what I'm going to do is I'm going to solve the equations for y double dot, x double dot, and b, and a. Alright, we'll put a simplify around here. Well, let's put in values. This gravity would be 9.81. Semicolon means don't print it. Let's see, I need the mass of A. And let's see what that was. Mass of A is, B is 10 and A is 22. B is 10 and A is 22. Okay, so let's see, x double dot is negative. That's kind of what I expected. It would be sliding down. Y double dot is positive, which is what I expect. The normals are both positive, so it doesn't fly up off the table. So that was the accelerations. For the second part, if you notice, it's a time spanner. So if you look at it, it wants to, I found the accelerations are all constant. The velocity of B relative to A at time equal 0.5. The relative is x double dot, and so I can just, since it's a time spanner, I can integrate that. So x double dot, if I integrate it, it's a constant. What is it I want to find? The velocity, I think, right? Yeah, the velocity of B. Okay. And because the acceleration is a constant, right there, I can use the equations. The V of B is the initial VB, which is 0, plus the acceleration. So I'll paste it in. The acceleration of B, this is the relative acceleration, times the time, 0.5 seconds. So the relative velocity is a -6. So if you look back at the figure that I drew, the x dot appears to be a -6, so it's getting smaller, so B is actually sliding down the incline, as you would expect. The total acceleration of B is going to be this expression right here. So you can plug that into your Mathematica. Right here, acceleration of B. So the acceleration of B is this, and we'll plug in the known values. So we'll plug in x double dot is a minus 12.45, and plug in y double dot is 6.995, and bingo. So your acceleration would be 5 to the right and a -7 down. If you wanted to find the magnitude, you could just square those and add them together. So that's the solution to that one.